later in YouTube than the people that is actually connected.
Yes, yes.
If you promise to do not use it against me later on, that's fine.
We are online on YouTube.
How much time do we have?
1 hour.
Okay.
45 minutes, 1 hour. Then maybe people will have questions and you can respond, you can answer.
Okay. I think I have something like 45 slides, and that is probably a little bit too much for 1 hour.
Hola a todos. Hola Pedro. Eivind, you can share the presentation now. It's okay. Bueno, vamos a comenzar con la presentación. Muchas gracias a todos por su asistencia. Este es un seminario que se da a través de a través del diploma de postítulo de túneles y espacios subterráneos, que pertenece al área de educación continua de Ingeniería Civil de la Facultad de Ciencias Físicas y Matemáticas de la Universidad de Chile. Anteriormente tuvimos a John Kanechiro, un geólogo norteamericano. Hoy día nos hemos cambiado de continente y tenemos como invitado a Eivind Grov, científico jefe de SINTEF, un instituto de investigación noruego, y profesor también de la Universidad Noruega de Ciencia y Tecnología, donde dicta conferencias y supervisa estudiantes de máster y doctorado. Eivind es expresidente de la Sociedad Noruega de Túneles y es miembro honorario de esta sociedad. También es expresidente de la Red Noruega de Túneles, ¿ya?, que es el organismo que dirige Arild Sodik, que nos acompaña también, y que en los últimos años ha estado realizando diversas actividades en Chile, tanto profesionales como académicas, ¿ya? Eivind también es ex vicepresidente de la Asociación Internacional de Túneles, ¿ya?, y participó durante 6 años en el Consejo Ejecutivo, y hoy día es miembro honorario de la misma, de la Asociación Internacional de Túneles. Eivind ha ocupado numerosas funciones en organizaciones internacionales y actualmente dirige un grupo de trabajo en la Asociación Internacional de Túneles relativa al uso del hormigón proyectado. Y Eivind también participa en la Sociedad Noruega de Túneles. Así que bueno, vamos a comenzar con la presentación. Pueden ir dejando las preguntas en el chat y al final de la presentación vamos haciendo las preguntas y Eivind nos las va a responder. Eivind, you can start, please.
Thank you very much. Good afternoon, everybody. And I was about to say it's good to see you all, but unfortunately I can't see anyone. Although this situation, I'll give you an introduction to the Norwegian tunneling. First of all, I'll introduce you to two bodies that we have in Norway with respect to promoting tunneling, both domestically as well as internationally. First of all, we have the Norwegian Tunneling Network, which this presentation is made on the basis of. It is actually a subsidiary of the Norwegian Tunneling Society, and the reason why we established this network was to engage members who are interested in international cooperation, and we are altogether covering the entire value chain of tunnel construction and operation, and also including, of course, design and different types of services. We have consultants on board, manufacturers, contractors, academia. So the entire value chain. The Norwegian Tunneling Society, on the other hand, is a much older organization. It was founded in 1963 and was one of the who took initiative to establishing the International Tunneling and Underground Space Association under the short name ITA. And today it has something like 1,100 personal members and approximately 100 member organization. This is more an organization that is established to promote, to drive the tunneling technology forward, and to distribute competence and knowledge within the organization, and also take care of how the greater society is actually looking at the tunneling industry. Just a short update on the productivity of the tunneling industry in Norway. Today, or in 2022, the total output was something like 5.1 million cubic meters of solid rock. This is equivalent to approximately 69 kilometers of tunnel. Out of this, about 3.2 kilometers was actually bored with TBM. The rest is conventional drill and blast, which is today even the most dominating excavation method in Norway. A total of 24 different contractors were employed in the civil tunneling. Mining, neither above or underground, is not included in these statistics. And you can see that from the 80s and 90s, where the output was approximately 4 million in average, we had some big peaks back in 2016-17, where we reached almost 8 million cubic meters of solid rock for civil tunneling. Today, we are back almost on what it used to be, but still slightly above the average. And there is a short translation of each of these different colors on the graph. So if this is going to be distributed, you will see underneath the translation of these names. And for those of you who have had the chance to go and visit Norway, you have probably seen that when you are leaving Norway on the airport, you will see souvenir shops which are selling trolls. And in the Norwegian fairy tales, these trolls, they were actually always living in beautiful mountain halls. So it is a logic and natural cause for Norwegians to make tunnels and underground space. Since 1884, something like almost 1,250 road tunnels have been built. We have approximately 150 being planned, and 50 approximately are under construction at the moment. Soon we will have something like 40 subsea road tunnels in operation. As you know, and as you will see on some maps later on, the Norwegian landmass is cut by deep fjords, which are cutting deep into the landscape, and this makes for sure the need of subsea road tunnels. A big project named Rogfast, which is a 27-kilometer subsea road tunnel with 2 tubes, reaching down to approximately 390 meters below sea level, is actually ongoing in construction phase. When it comes to railway tunnels, the first big project was actually the Oslo-Bergen Railway, which was finished in 1909, and it consists of 182 tunnels. And these are some short and some longer ones. But at that time, that was really high achievements for the industry. The Follobanen, which is the latest big project within railway tunnels, was opened in December 2022, which is 2 times 20 kilometers TBM bored tunnels. We have something like 750 railway tunnels in Norway today in operation. And totally, when you add railway tunnels to road tunnels, the approximate length is around 3,000 kilometers. In addition, and in particular in Oslo area, we have some metro tunnels, but they are not that many. If you look at caverns and tunnels in general, the hydropower era started in Norway following the Second World War. And today we have something like, and this is a guesstimate, around 5,000 kilometers of hydropower tunnels. More than 200 powerhouse caverns have been built to serve these hydropower plants that we have. If we look at oil and gas storage facilities, we have around 60 caverns, particularly designed and made for storage of oil and gas. The number of caverns for water storage, sewage treatment, parking lots, and so on and so forth, we do not have, the number of those. There's a big bunch of that kind of purposes. I have added a photo collage below where you see some of the uses that caverns are made for. In the Cold War era, in particular, we made the combined civil shelters with sports arenas, and those you will see some of on the left-hand side of the slide. In the middle, you will see a map of Trondheim, and you will see that there we have 2 large storage facilities of drinkable water. On the upper right-hand side, you see some slides showing the construction of the Gjøvik, and the Gjøvik in operation mode with fully packed with some kind of entertainment thing going on. On the right-hand lower corner, you see some interior of hydropower plants. In the middle, in the lower part, you see also some combination of civil defense shelters and sports arenas. There's a good number of underground facilities for all these kind of purposes. The principles in all of these different tunnels and underground caverns is that the concept is to target short construction time, low construction cost, low cost of operation and maintenance. And what we in particular do is that we consider the rock mass as a construction material, and we integrated this into the underground structure itself. So whatever we need to add to the rock mass itself in terms of support design or reinforcement, we add what we need to produce the required factor of safety for that particular purpose this tunnel or underground space has. And conflict reduction and efficiency is supported by a risk-sharing contract system and contract incentives. We will come back to that later on. We understand that the tunneling in Chile is promising at the moment, both for the mining and for the civil tunneling purposes. So the question then would be, can an approach from abroad be implemented in Chile? And the first reaction is that each project, and I would say each underground project in itself, is a unique project. Unique in the terms that the ground conditions are different from place to place, and the rules and the regulations may not necessarily be compatible. More important obstacles could be, from our experience that we have, that local traditions, decision-taking cultures, and normal human resistance to change could hamper the development. And to some extent, this may completely overrule and stop the use of different approaches. And that's a pity if such happens. Common tunneling challenge everywhere in the world, that is that no matter where we are going, being Chile or Norway or wherever, there is a frequent change of ground conditions within an often very wide range. And we have to have a concept, we have to have a system which is actually capable of taking care of these frequently changing ground conditions. So we can challenge this in two ways. We can apply what we consider as a worst case rock support for the entire tunnel. That means a standard rock support, no matter what kind of ground conditions that we have. The other solution would be to adapt the support along the tunnel to whatever is the minimum necessary and safe tunneling and operation conditions. We sometimes call this for an active design because the design is developed as the rock mass is encountered during the excavation work. Both are possible and will work. However, one may see that, or one may experience that there could be a time and cost difference between these two approaches. We have to take, when we do this adaptive approach, we have to take the work changes into account when we implement the support. And we have to do this regardless of rock conditions and groundwater. What we see internationally is that there is a sort of over conservative lining solution, which is sometimes applied without actually taking into account what is really required. And honestly, to you, we have seen this growing in Norway as well. But I hope that the new era that is coming, which means that we have to reduce the emissions from the tunneling industry, will also mean that the solution with cast-in-place concrete linings or precast segments will be reduced in quantity and representation in the tunneling business. We have seen this being successfully applied in various parts of the world, particularly in the Nordic countries, and I would point specifically to Iceland and the Faroe Islands. But we have also seen this approach being included in tunneling in Hong Kong recently. And some people tend to believe that the ground condition in Norway is always very good rock mass conditions. That is definitely not the case, because as is necessary in many places around the world, we are also facing the challenge to meet changing ground conditions, as we have been discussing already. The rock burden or the rock cover could in many cases reach as much as 1,500 meters, which means that we also have to face rock burst and squeezing. But at the same time, these stressed areas can also be faced, and particularly at shallow depth. We have had tunnels in Norway with a groundwater head of 1,000 meters, that is 100 bars, which is really something to fight with when you have excessive leakage and you need to grout it by pre-excavation grouting. If we look at some moon landings in tunneling in Norway, I would say that the high performance TBMs that were developed in the 80s, which were made particularly for hard rock tunneling with up to 32 tons per cutter and 17 to 18 inches cutters, was something that was developed to satisfy Norwegian owners. We have headrace tunnels in Norway for the hydropower development with more than 1,000 meters water pressure. I think the largest was Nye Tien, which was put into operation some 10-15 years ago, where the water pressure was slightly above 1,000. I think it was 1,040 meters. We have tunnel piercing, which is a kind of a specialty that originally came from the hydropower development, but has been used recently also for landfall tunnels in the oil and gas business. And the highest water depth was actually 175 meters for the landfall tunnel for Troll. We have chilled or cold storage facilities for LPG at down to minus 42 degrees Celsius. We aim at, or the idea now is to try to look at hydrogen, ammonia, CO2, to mention some, where we have to go even further, either in temperature or in pressure. We developed air cushion chambers and water curtain, which have been used in hydropower development as well as for oil and gas storage facilities. The Gjøvik Olympic Hall, to be mentioned, is 62 meters in width, which is, as far as I know, the largest man-made cavern in width so far. And as I said, the subsea tunnel, Rogfast, down to 390 meters below sea level. Wet mixed spray concrete is something which we have been working a lot with in Norway. And now we are looking at a sprayed concrete, which is hopefully a watertight sprayed concrete. And in that case, it can be used also as a water protection system. Equivalent time system for risk sharing, which is something that I will come back to later during the presentation, and high pressure pre-excavation grouting. These are some technological moon landings that at least I have seen as something which has come out of the Norwegian tunneling industry. and which can be made available all over the world. As you can see on the pictures, there are lots of reasons in Norway for underground facilities. The coastal line is something like 100,000 kilometers long, with deep fjords, which, as I said earlier, is cutting into the landscape. We have snow avalanches, we have rock falls, and a lot of natural things that is taking place in these fjords. And going underground, I mean, not only because you need them for transport of goods and people, but also due to the fact that in the future there will be more focus on out of sight, out of mind, or not in my backyard. There are lots of surface facilities that successfully can be put underground. And underground, everything is protected from earthquakes, from tsunamis, and from terror and sabotage and unfriendly actions, which we see in the global societies these days. If we look at the geological map of Norway, which you can see on the left-hand side of the screen, as I said, high mountains, deep fjords, and these fjords are typically all fault lines which are cutting the landscape. Long coastline, probably like you have in Chile to some extent, but maybe slightly smaller scale. And this landmass has been subject to faulting, to metamorphism, to glacier periods, to overtrusting, stress concentration, and stress reliefs. So it's a landscape which have been treated not very well from the natural environment which it has been a part of. We have Precambrian rocks at the west coast of Norway and in the southern part of Norway. We have Camerosiliurium rock, and particularly is this in the Oslo area. We have the Caledonian thrust system, which is actually cutting through the landscape from the west coast up through Trøndelag, Nordland, and to the far north. So the main philosophy in the Norwegian tunneling is, as I said, that rock is a part of the construction material. We have a very systematic approach using, to some extent, risk and opportunity assessment. And the fact that we are able to, in the tunneling industry, to identify the challenges and the risks that we see or foresee when it comes to tunneling a certain section is important. It's important because then we can do the measures and the things upfront on what is actually needed to reduce the risk, instead of just dumping right into it. Over the last years, of course, life cycle cost assessment has become a method that is used, particularly when we look at different solutions for water and frost protection, for example, but also on the major part of installations in railway and road tunnels. With what we see, the UN goals, there has to be a cut or a reduction in the CO2 emission from the tunneling industry. And by setting or putting the environmental effects in focus, for good and for bad, that would need to be a source to promote innovation in the tunneling industry. And the supercon, which I mentioned earlier, the watertight sprayed concrete, is one of the things that we are looking at the moment to be able to reduce the emission and be a better caretaker of the environmental impacts that tunneling is actually causing. We have something, or the Norwegian Public Roads Administration has been good at preparing guidelines and handbooks and all sorts of things which are related to road making and tunnel making. And to some extent, these are quite specific, but on other aspects, they are useful for other types of underground projects as well. And in this context, we will look at some of these aspects that are presented in one of these handbooks, namely one which is called Veitunneler, road tunnels, the handbook on road tunnels. And we will look at the three aspects that are listed here in red color: geometry and design, work ahead of tunnel phase, rock support, water and frost protection. During the planning stage, it is in Norway at least, and I would guess that this is something which is not very particular for Norway, but we always start with a desktop study for a project, collecting available existing information from neighboring tunnels and caverns or other projects that we have been involved in, and so on and so forth. A geological surface mapping would always be mandatory, coupled with, of course, aerial photos, because in the Norwegian landscape, which has been eroded by glaciers, we can easily see structures in the landscape because weakness zones, etc., has been eroded whilst the fresh rock is standing up. So it's quite easy to see where do we have fault zones, where do we have weakness zones, and so on. It follows with site investigation and sampling. And I would say that in many cases, stress measurements are kind of vital information that is sought to be able to, first of all, put the cavern or the tunnel in the right place and secure it for stress regimes. But also it is a guideline, the stress situation is a guideline for how we could actually execute pre-excavation grouting. And then, of course, in situ and laboratory testing follows, numerical analysis, and we are very often using the Q system for mass classification. We have presented something in SINTEF, which is called tripod, which is actually a combination of doing measurements upfront, inserting these measurements and testing into a numerical model. When the excavation starts, we do extensometer readings, we do long-term stress measurements, and we feed all these new information into the numerical model, and then we are able to calibrate the numerical model. And then it goes back to the start again to modify the model and to see if the reality fits with what we actually predicted during numerical models. Of course, in Norway, BIM, three-dimensional BIM, has become more and more a must in tunneling works. And the way we can do it is like it is shown here on the screen. We can take the investigation and test results and implement those into the three-dimensional model. And we will then be able to see orientation of weakness zones, dip of weakness zones, and so on. And we can model our tunnel accordingly, if we have the flexibility. And that's important. When it comes to the construction site, of course, during the planning stage, we cannot pre-investigate to such a level that there is no more risk left. That is not a viable situation. That will be too costly, too lengthy, and you may not have full benefit of all this information at the end of the day. Thus, there must be some risk that we can handle during construction, and some of the means and methods that we have available for doing that is probe drilling ahead of tunnel phase. We can do it with the equipment that is at the tunnel boring machine itself, the tunnel bore rig itself, or we can do it as core drilling, but that is a little bit too long-lasting if you compare to what capacity you can use from the drilling rig. And mandatory in some of the Norwegian tunnels today is to use measurement while drilling. So all holes which are drilled, blast holes, core holes, probe drilling holes, and so on, are actually measured with measurement while drilling equipment. We tend to say that this method still is within what we call the observational method, which in my opinion means that we map what we encounter and we take the actions according to what we encounter. What we have seen recently is also the fact that all drilling jump boats today have cameras at the drill rig, so you can take photos from the tunnel face for each blast run. That is a great surplus to the mapping itself. Mapping is to some extent quite subjective because there's a geologist who is doing this, whilst photos which are taken are, on the other hand, objective. And also the scanning technology has improved over the years. So today all surfaces are scanned before and after sprayed concreting so that we know exactly the thickness of the spraying. This is a typical geological mapping that we do in Norway, with the geology as shown in the well, we can start from the top on the scheme on the left-hand side. From the top, you will see all the parameters in the Q system. Also, the length of, I think it's the probe drilling ahead of tunnel phase. You will see the geology in the second upper row, and then the suggested rock support measures. And at the bottom, heavy support if something else than rock walls and sprayed concrete would be required. That will be in the lowest row of information. As I said, one of the main tools that we have is probe drilling ahead of the tunnel phase to obtain information of the rock mass ahead of the phase using the measurement while drilling technology. But we have also seen that there are new technologies like TPS, like rock mass tomography, acoustic sounding, and similar measures, which are useful when we are, or when we expect that we have extreme poor ground conditions ahead of phase. Grouting or pre-excavation grouting is a must in Norway. We always have a pre-excavation grouting as the first line of defense when it comes to deal with water. And if we need something more than what we could gain from rock walls and sprayed concrete, spiling balls will be the first to come then reinforced ribs of sprayed concrete, pipe umbrellas to be installed if there is extreme poor ground conditions. We try as good as we can or as best as we can to avoid cast in place concrete linings in Norway. Ground freezing is another tool that we have at hand, but it has been used in very, very few cases. You will see a slide later on from the Oslofjord project where it was actually applied. And then, of course, it's interesting and it's important that we compare what we gain from the pre-investigation results and the measurement while drilling. And it may not be so that they are identical, but I think that the most important thing in this case is the precaution and the hands up on potential zones for decision making, so that we are able to do the decision making in good time before we enter into something which is of poor quality. On the left-hand side, there's a picture of ribs of sprayed concrete, reinforced sprayed concrete. In the middle, it's a picture of pipe umbrellas, and on the right-hand side, you see the three pictures on top of each other. This is from the Oslofjord tunnel and a subsea road tunnel, which was excavated back in the 90s, late 90s. What they encountered when they were going on a descent. On the upper picture, they came from the left-hand side, went down towards the right-hand side, and you can see that they encountered a weakness zone. This weakness zone was actually detected during the probe drilling ahead of tunnel phase, and it was of extremely poor quality. So they stopped the excavation. They decided to make a go around on a lower level, which you can see in the picture in the middle. And they used the freezing technique to stabilize the weak zone, the fault zone. And after freezing, they concreted the whole thing. And finally, when this was completed, they opened the tunnel in this area and used the go-around tunnel that they had, the bypass tunnel, for other purposes. So this was really a school example on how to react and what to do when the probe drilling ahead of tunnel phase was showing something of very, very poor quality ahead of tunnel phase. As I said, water control in Norwegian tunnels, the basics philosophy is pre-excavation grouting as first line of defense. This is due to the fact that in many cases we have experienced that water leakage that comes through the rock and enter into the tunnel is causing a dewatering of groundwater. What we have today is a tool to decide the maximum allowable inflow level to a tunnel, and this level is based on calculations and modeling of what is on surface with respect to constructions at the surface or flora and fauna at the surface. How sensitive are these different things with respect to a lowered groundwater level? And from this, we get the maximum allowable inflow level in the tunnel. And this level is then decisive for the grouting effect that we are using. And during the excavation itself, the construction phase, we have tidy control on the actual water inflow to the tunnel, so that we are monitoring and measuring the inflow, and we are also monitoring and measuring eventual incidents at the surface, fracking on buildings, for example, or piezometric levels in the ground. The Norwegian Tunneling Society has presented to the International Tunneling Society through ITA a number of publications, and one of them is named rock mass grouting. It holds a good deal of information for the tunneling business with respect to water control by pre-excavation grouting. I don't think I go any further into the details on this. Water and frost protection. In a country like Norway, where we have nice and warm summers, we also have nice and cold winters. And in the case of the winter, in many tunnels, we have to install frost protection systems. Therefore, we call it water and frost protection system. In principle, all inflow water that are within the allowable level will be collected through drain system. So it will be collected between the water and frost protection system and the rock mass itself. And it will be drained to the surface, either by gravity or by pumps. Then we have a number of solutions to actually install these water and frost protection systems. They could be kind of membrane types. They could be PE foam, which is an insulation material which need to be fire protected. It could be shotcrete and sprayed membrane. And of course, also the heavier stuff like concrete elements and membrane and concrete lining. But if we concentrate on the 4 first bullet points, I think that would be a great benefit. Even though we have these sort of custom designed solutions, they have shown to be quite robust. They are withstanding the pressure and suction forces that comes along with heavy transport, which is driving through a tunnel. And they could also withstand the traffic accidents and collisions. May deform something, but then they should be easy to repair. And they are fire safe and cost effective, of course. So this is a nice picture of a tunnel with a new type of water and frost protection system, which, as you see, do not necessarily need to have a sprayed concrete fire protection system on top. So some words about risk sharing. And I've said it already a number of times, that tunneling is inevitably associated with handling of uncertainties and risk. And the risk is logically associated with geological conditions, and the risk can be significant. We have seen a number of occasions in Norway and elsewhere around the world on projects which have had cost overruns and time overruns. And a number of claims which have gone to court are based on unexpected geological conditions. This is way too often claimed to be the case. And since each and every underground project is unique, we have talked about this earlier, surroundings, geology, owners, and so on and so forth. The risk in each project, each tunnel project, is also unique. And therefore, the contracts that we are establishing, they must be unique and fit for purpose for that particular project, which it is designed for. This is a compilation or a comparison between different types of contract formats. where we have tried to show the owner's risk and the contractor's risk and the project cost. And we see that when we use a typical unit rate contract, as we normally do in Norway, that is to some extent the tool to reach as small project cost as possible. When it comes to this risk-sharing principle that we have in Norway, we normally say that the ground conditions belong to the owner's part of the risk picture. The owner is responsible for the ground conditions. The owner provides the ground. The owner is responsible for site investigation, and consequently, this should belong to his risk portion for the construction of the site also. On the other hand, the performance is the contractor's risk. The contractor is responsible for efficient execution of the works. Execute works according to technical specification. And in Norway, where we have this unit rate contract format, the contractor is reimbursed according to tendered unit rates for work actually completed. And then we have a tool at hand to adjust the construction time based on standard capacities and the unit rates that are the number of the units that are in the contract. So the contract documents must reflect the best estimate and judgment of the ground conditions at the time the assessment is actually done. I have a strong, feeling that in many cases, there is some controversy between the tender documents, that is the number of units, the time which is in the contract, and the geological report. If these three do not paint the same picture, there is some tricks in the system. So be care of that particular thing. And the contract itself is just a mitigation tool. And it has to have relevant regulations so that we are able to deal with the actual situations on the site. And we will see that in a few slides. We have already stated that it's not viable to investigate to such a level that all risk is ruled out. But we are able to reduce the risk to an acceptable level. An acceptable level is also something which is not straightforward, because different persons, different companies may have a different opinion on what is acceptable level. But what the contract has to do is to have a fair and appropriate risk sharing between the owner and the contractor. And we have also way too often seen that the contract documents, when they are out for tender, may not necessarily give the contractor the possibility to price the risk sufficiently. And way too many contractors jump on this without taking good notice of it. And then, of course, the contractor is in a big trouble if things goes wrong. The risk that we have for a project needs to be identified and managed within acceptable level for all parties in the project. As said already many times, we have changed conditions in a tunneling project. That's almost inevitable. But we can differentiate between what is foreseen and expected, what is foreseen and unexpected, and what is totally unforeseen. when we have a situation which is foreseen and unexpected, the risk-sharing principle ideally eliminates most discussions about change ground conditions. And then it only becomes a calculation on the number of items which have been used in the project, the payment, and the construction time that follows this. It's kind of a balance sheet for cost and for time. We take the next, I think. If there are foreseen but unexpected conditions, if such conditions occur, the important thing is then that the contract has and includes contingencies and clauses that could together hold a solution in the contract. It may not be as easy as when it's foreseen, unexpected, but the contract must have conditions and clauses to be able to find a solution for the situation. On the other hand, if truly unforeseen conditions occur, unit rate contracts may not provide a magical solution. And that will not be done by a fixed price contract either. The success of such a situation depends on the ability and the willingness at the site between the contractor and the owner to solve the problem, both technically and contractually and cost-wise. And in the case of a truly unforeseen situation, the owner sits with the majority of the risk because it could lead to a bankruptcy of the contractor, and then the owner just has an unfinished product left. It is important that at the site we have representatives for the owner and for the contractors who have authority to take decisions. Take decisions which have significant influence on the cost and the time, both technically and contractually. And it's important that we respect each other's tasks. When it comes to one-time owners, they may have a totally different perspective on risks in tunneling, because they may have one project that they would like to tunnel, and then the situation is different from a multiple tunneling owner. There is a need that at the tunnel phase, when the contractor and the owner meets and are doing decision taking on rock support, on permanent rock support or reinforcement, on pre-excavation grouting, on additional investigations to be done, and similar things. This call for experienced people to be at the site throughout the project organizations and throughout the duration of the construction time. They have to be familiar with the contract format so that they could enable discussions and agreements being made as soon as possible and with confidence when such situations arises. The equivalent time principle is something particular. What it actually does is to convert quantity, like quantity of rock balls or sprayed concrete or this or that, and into a common unit, which is number of hours. So pieces and cubic and square meters and so on and so forth becomes hours. Each item for those activities which is actually hampering or delaying the tunnel advance has a standard time estimate for the performance of one unit. And if you see in the bottom on the slide, there is a table, and this table presents some equivalent times or capacities. For example, rock balls up to 5 meters, the equivalent capacity is 12 pieces of bolts per running hour. Sprayed concrete, 6 cubic meters per hour. Concrete lining, 0.1 meter per hour, and so on and so forth. So these capacities are used in a balance sheet to find the difference between what was in the contract, the number in the numbers or the units in the contract, and the actual numbers or actual units which have been produced. And then there is a difference up and down, and the contractor is entitled a duration of extension if it goes beyond, let's say, 1 to 2 weeks per year of construction time. So this is a way to use the production to extend or shorten, if that is the case, the construction time. This is just a sample tabulation that is showing how this whole thing is put together. I don't think I need to go through it, but you see all the activities on the left-hand side. You see the contractual quantities. You see the time equivalents in shifts per unit. So at that time, this was a slightly different build-up. Contractual calculated time, actual quantities, calculated time for the actual quantities. And it comes to a difference, which is up or down, and it could go to a time extension or a reduction of construction time, if that is the case. What we have seen is that in many cases, even a typical straightforward unit rate contract may not necessarily be the best for a project. What we have been looking at for some project is what we call modified, hybrid, or adjustable fixed price contracts, which means that a certain part of the contract can be a fixed price contract. Typically, those items which are best known by the contractor compared to what an owner could know, and which could then be the risk-taking by the contractor, whilst those elements which are related to typical geological conditions should be taken and should be the risk of the owners. What we have seen is that the Emerald book that came out just recently has, to some extent, this kind of hybrid contract format. So this is very interesting for the future. When it comes to the ground investigations as an important part of our tunneling project, as we have said, you cannot investigate to such a level that all risk is ruled out. There has to be some risk residual. But conducting dedicated investigations means that every single investigation measure, shall have its particular purpose, which means that you should, if you decide to do something, defend strongly why do you actually have to do this type of investigation at that particular point. Because most of it is important, most of it is indirect methods, and it means that you have to understand the geological features from a tunneling perspective to be able to have some benefit of this information. As mentioned earlier, probe drilling has been acknowledged as an investigation method in Norwegian tunneling, which means that yes, we cannot properly do pre-investigation, so we leave to the probe drilling ahead of tunnel phase to actually give us more information whilst we are doing the tunneling works itself. Active design, I touched base on active design or adaptive design in the very beginning of my presentation. It's related to, first of all, groundwater control. Probe drilling ahead of phase is the key, and we are always leaning on pre-excavation grouting. What we have seen is that to some extent we are able to document that we are reaching down to 2 liters per minute per 100 meter tunnel in the residual inflow, which means that it is dust dry in fact. In some cases, we are able to improve the permeability with the power of 2 in meters per second. Cautious blasting, that means aim at reducing the cracking, the secondary cracking. To some extent, I think that research has not been done properly with respect to the interface between the secondary cracking, that area, how deep is it, and the consequences on support, for example, the consequences on water inflow. There is a lot to gain by cautious blasting to produce a smooth and even surface with as little secondary cracking as possible. We do empirical guidelines combined with analytical and numerical modeling. Q system, RMR, for example, are typically included in the tunneling design. And when needed, we also take into account numerical modeling. And I mentioned the tripod for you earlier. That is a typical example on how we combine different types of investigations. Observations and monitoring. Many do believe that monitoring belongs to NITM, but we see that over the last years that this is also becoming more and more important also in hard rock tunneling, that we do monitor what is actually taking place over time and not just look at what was actually instantly happening when we blasted the tunnel face. One thing to keep in mind is that the drain structures means that we do not need to make a watertight tunnel. We have to adapt the water inflow to what is actually on the surface, what is the groundwater level, and do not disturb the groundwater level, but do not necessarily make it a yellow submarine in the rock mass, because that is in many cases not necessary. Drain structure means that we are also controlling and handling the discharge of water. Primary support approved as permanent support. This is something which is of interest, where there is significant savings, because in some places we see that primary support is done by means and tools and things that do not fulfill the technical specifications for permanent support, which means that you have to ignore what you have done in the later stage and supplement with a full permanent support installation. If we use primary support, which is actually fulfilling the technical specifications for permanent works, then we also include that into the total permanent support works for the tunnel itself. Yeah. These I think that we have been touching base on already. Probe drilling has been mentioned, and probe drilling could be 2 to 4 to 6 probe holes ahead of the tunnel face with various lengths, depending on where is your tunnel face at any point in time and you can tailor-made the probe drilling system that you are using. When you expect that there is a fault zone ahead of the tunnel face, then the number is increased, and it's going back when expect to enter into better rock mass conditions. And this picture shows just some examples on how you can do that. In many countries, in many countries, there are kind of lots of people at the tunnel face and maybe old equipment. That is because labor is cheap and equipment is expensive. In the Scandinavian countries, labor is expensive and equipment is cheap. So that means that we have high capacity, state-of-the-art equipment along the whole line of equipment that is needed. Multi-skilled workmen at tunnel face, who are enabling high utilization of this equipment, and also on-site decision taking. This is not limited to drill and blast, not by any means. TBM application is also one of, or a part of the concept, as something like 300 kilometers of TBM tunnels have been constructed in Norway over the times. We see that more and more data is being recorded, not only for grouting, as is written here, but for all sorts of activities. So from a drilling jumbo, from a grouting jumbo, from a sprayed concrete jumbo, there is a large amount of information which is coming out. Information which could be taken care of and could be used in later machine learning and artificial intelligence for the tunneling industry. This is moving slowly in the right direction now. In a broad perspective, there are probably more common interests at the construction site than interest of conflict. This is not what we typically see, but I think this is basically the case. So we have to respect each other. We have to respect the different roles that we have, and the tunneling is a complex process. And in that sense, constructive cooperation between all the representatives of the involved parties is actually needed at all times in the project. We should be much better to solve conflicts at the construction site by discussing and negotiation, and try to avoid not ending up in, or try to avoid to end up in court. So these are the concluding comments from this. I think the most important bullet point is actually the one in italic at the very bottom, saying that making decisions by right persons at the right place and at the right time. It is, as I said, often claimed that the Norwegian tunneling philosophy is no big deal in Norway because the rock mass quality is so good. But in my opinion, there are a number of regions around the world who have similar ground conditions, and this is not typically something which is only valid for Norway. But as I've said earlier, it's basically a matter of frequently changing ground conditions and adapt to this situation. Contract, procedures, and cooperation to enable adaptation of this. And that was all.
Thank you for the presentation, Eivind. Thank you very much. Now I'm going to close the recording on YouTube so that people in this room can ask questions and participate more